Hello everyone, this is Professor Keen. I will be talking today about centripetal force and acceleration. The reference for this work is A Student's Guide, Volume 2, Chapter 24, which is from Newton's Principia, Book 1, Section 2. So once again, the topic is centripetal force and acceleration. This will probably take a few lectures to go through this, but I'll get started in this one. So in this section of the text, what Newton does is he describes the kind of motion that a body will undergo when it is experiencing a centripetal force. Okay, so Newton describes the motion a body undergoes when experiencing a centripetal force, right? And what he's eventually going to do is he's going to turn this around and argue that if a body exhibits a certain kind of motion, if it exhibits a certain kind of motion, one can then infer that a centripetal force must be acting on it. So he's going to work this, eventually he's going to work this backwards. But right now what he's saying is, let's consider what kind of motion a body experiences when it's feeling a centripetal force, and eventually he's going to look at the motion of bodies and say, wow, it's experiencing that kind of motion, it must be experiencing a centripetal force. What he's going to do is he's going to then argue that, first of all, planets, Mars, Jupiter, Saturn, and so on, are experiencing a centripetal force that is directed toward the sun. And he's also going to argue that by looking at the motion of the moon, we can conclude that it too is experiencing a centripetal force that is directed toward the Earth. So that is eventually where he's going to go with all this. So let's remind ourselves what the definition of a centripetal force is. So Newton defined a centripetal force. A centripetal force is a force acting on a body. So a force acting on a body that is directed toward a point as to a center. Right? Directed toward a point as to a center. And it's good to keep in mind that such a centripetal force that is directed toward a point as to a center can be a pull, but it doesn't have to be a pull. It could also be a push. So remember that it could be a pull. So for example, if you're holding onto a string and you're swinging a rock around, the tension in the rope is producing this centripetal force that is acting inward, right? In this case, the centripetal force is produced by the tension in the string, and that would be the case of a pull creating a centripetal force. But it doesn't need to be a pull. It could be a push, for example. It could be a push, and the example I gave before was a hockey puck, but it doesn't necessarily need to be this. You could think about, a soccer game, and so here's a soccer field, and there are goals at each end. And if everyone on one team is trying to kick the ball toward a point in the goal, so here's the ball, and someone's kicking it, and that kick is toward that point in the goal, and then maybe later on, when the ball gets over to here, someone, again, is kicking it toward that point. And maybe later on, when the ball is over here, someone is kicking the ball toward that point. All of these forces are directed toward a point as to a center, and so that would qualify as a centripetal force according to Newton's criteria. So these two examples illustrate, I guess, two important features. One is it can either be a pull or a push, and secondly, it can either be a continuous force or it can be discrete forces. So in this case, the string is continually pulling on it. And in this case, you have individual soccer players kicking the ball at particular instants toward a point, and both of those qualify as centripetal forces according to Newton's criteria. Okay, so now, having given that background, let's jump into section 2 of book 1 of Newton's Principia. So he begins with a proposition. He calls this proposition 1, Theorem 1. So remember, this reads a little bit like a math book, right? So let me just tell you what proposition Theorem 1 is. I'll just quote it for you, and then we'll explain what it means. So the areas, as Newton says, the areas which revolving bodies describe by radii drawn to an immovable center, toward an immovable center of force, first of all, they do lie in the same immovable planes and secondly, they are proportional to the times in which they are described. Okay, so he's saying a couple of things here. So he's imagining that you have some body or some object. You might imagine an object flying through space, maybe an asteroid or something. And if this object is drawn toward a center of force, so that is, if there's a centripetal force acting on this object, again, either a discrete centripetal force or a continuous centripetal force, then that object should exhibit two kinds of behaviors. First of all, the area which that object sweeps out, I'll explain what I mean by that in a moment. The area which it sweeps out, or what maybe a radius drawn from the center of force to the object, the area that sweeps out lies in a plane, and also the area is proportional to the time they're described. Okay? So in order to understand this better, what Newton does is he provides an example. And I have this sketch, this drawing up here that Newton gave us. And so I'd like to explain this proposition or this theorem in terms of this diagram that Newton gives us. So he's going to prove this theorem. And I think in the course of proving this theorem, you'll understand why this is important. Okay, so let me point out a few things that are important in this diagram. So one should imagine, I'm going to draw on this. So this right here, this point S, this is the center of force. The center of force. In other words, it's the point toward which the centripetal force is going to be acting. Okay? The object that we're considering starts out at point A. Okay? And one might imagine that this object had been moving along this line, and right now it's at point A and it's going toward point B. So this is the trajectory of the body. So it's going along in a straight line initially, and he's going to say what happens to it. Okay, now, so where does he go with this? So let's go back over here, and we'll make a proof of this proposition 1, theorem 1. How does he prove what he's claiming here? So here are the steps. Basically what he says is, let's divide time into equal parts. He doesn't say what the time intervals he's considering, so let's just call it delta t. This could be 1 second, for example. So imagine you divide time up so that you're checking it once every second. And what he's doing is he's saying at the initial time, this object, you might think of it as this is just like a ball flying through space. At the initial time, it's at position A. And then we're going to ask what happens to it at a time delta t later, maybe 1 second later, it will have moved up to point B. Okay, so that will be a time interval delta t. So during the first time interval, the object or the body moves, let me go back here, write that a little nicer. It moves from point A to point B, right? All right. Now, so it moves along, maybe I should say, along the line segment AB. That's what's going on here. Okay. Now, by Newton's first law, an object in motion tends to stay in motion, and an object at rest tends to stay at rest. So if there were no forces acting on this object, it would just go in a straight line from A to B. And once it gets to B, it would continue on to point C if there was no force acting on it. So by Newton's first law, if no force acts on the body, let me give myself a little more room here, acts on the body, if no force acts on the body, then it would, arrive at point C in the second time interval. Delta t, right? So if this is maybe 1 second, in 1 more second, going in a straight line, it would go right up to there. So this line segment BC would have the same length as AB. So AB line segment would be equal in length to AC, that line segment, right? So that is using Newton's first law. Okay, makes sense so far? Now, suppose, though, instead that at the moment this object arrives at point B, there is a centripetal force that acts on it and pushes it straight toward that point right here, straight toward that center of force. So at point B, a centripetal force, you might think about this as just a sudden kick, instantaneous kick, acts on it, on the body, and it's directed toward point S, right? So that's what he's imagining happening. And what happens when this pushes on it toward point S? Well, it would have gone up to point C. So that's the motion it would have experienced. But because there's a force acting on it in this way, it changes its momentum. It changes its momentum in this direction, right? So by Newton's second law, there's an additional motion that is imposed on it in the direction from B toward V. So now it has sort of two motions. It has its original motion that it was going to have, going from B to C, and superimposed on this, it has another motion that wants to take it from B to V. And as a result, we can draw a parallelogram like this, and the body, instead of arriving at little c, it arrives at point big C. So point big C is the location it arrives at. So it goes along this trajectory first, from there to there, and then it goes from there to there. Okay, so the force, and this is, I'm actually invoking, so by his corollary 1 on page 266, remember when we added together two forces, a force that's a motion that would have gone that way and a motion that would have gone that way, you can construct a diagonal like this. So that's what we're doing. We're using that corollary. By corollary 266, the motion of the body, so the body moves along B capital C, so that's this C right there, along BC, due to the combination, due to the inertia that it would have had, plus the motion acquired by the force. At point B. That it felt at point B, right? So instead of going up to point C, it goes over there, okay? Now it's important that the additional motion is directed toward the center, and that this line right here, it's going to be important that this line right here is parallel to that line right there. We'll come back to that in a minute. That's the additional motion that's acquired by it, okay? Now, notice a couple of things. So notice that the line BC, this capital C, the trajectory like this, that line lies in the same plane as line, or maybe I should say as the triangle SAB. So if originally it was moving along this line, if we draw a triangle right here, that forms a plane, and that new line lies in the exact same plane. Think about the surface of your computer screen. This triangle lies in the surface of the computer screen. That line right there lies in the exact same plane. It's not tilted out of the screen toward you or into the screen away from you. It lies in the exact same plane, right? Why do we know it lies in the same plane? Well, because there is no motion acquired out of the plane. If its motion was originally in this direction from A to B, and it would have ended up over here at little c, and there's a force that is itself acting in this plane, that means that the new motion acquired still lies in the plane of your computer screen or your paper, whatever you're looking at this on. So the total motion it's experiencing is a sum of one motion that lies in the plane and a newly acquired motion that lies in the plane. And so this trajectory still lies in the exact same plane. This is the point that he is trying to make in the first part here. If you think about the area, this area ABC, if this line from S to A kind of sweeps out this area as the body moves from A to B, and then it moves along here, that new area from S to B to C, that area also lies in the same plane as the original one. So the areas which revolving bodies describe by radii drawn to an immovable center of force do lie in the same immovable planes. Okay, so we have just proven, or we have just explained, Newton's first, point in proposition 1, theorem 1. Okay? All right, so tell you what, why don't we stop there? And I think I will pick up this discussion and explain point 2 in my next lecture.